Sum rule is true. Difference rule is true. All right, and you mark that C is false. Now, what is that note that you made off to the side? You wrote product rule and or chain rule. What did you mean by that next to part C?
So if you're trying to find the indefinite integral of a product of some function times some function, then you'd have to use the product rule, or use substitution if you don't know how. If you don't know the rule for the antiderivative for that function.
Okay. All right. So let's actually talk about that for a bit. So first of all, there is no product rule for antiderivatives. You might have been confusing that with derivatives. Remember, the product rule for derivatives is f prime times g plus f times g prime. But the situation is even worse for antiderivatives. For antiderivatives, there's no product rule at all. For antiderivatives, there's no product rule at all. So that wouldn't be one of our options. And then as for the chain rule, we probably shouldn't call it the chain rule because the chain rule is a name for differentiation. I think you also, when you were talking about that a second ago, you called it maybe U substitution, so that would be a better name. But there's no particular reason, so we might need U substitution there, but there's many, many different things you might use there. So some of those you might have been confusing differentiation and anti-differentiation. The chain rule refers to differentiation, not anti-differentiation, and there's a product rule for differentiation, but there's no product rule for anti-differentiation. I can see how you could get confused because there is a sum rule for both derivatives and antiderivatives. And there's a constant multiple rule for both derivatives and antiderivatives. But for products, there's only a product rule for derivatives. There's no product rule for antiderivatives. So how should you do that antiderivative? Well, you'll just have to be flexible and use some other approach. There's many, many different things that you might do to work it out. There's many different possibilities. Actually, just go back to my screen for a moment.
Okay.
Let's say you were trying to do this antiderivative. Well, what's the antiderivative of x squared?
That would be 1/3 x cubed plus c.
So can we just do this?
No.
Can we just take these two antiderivatives and multiply them? No, that would be the mistake. You can't take the antiderivatives separately. So what should you do instead?
We should combine the terms, the x to the fourth, dx, and then take the antiderivative of x to the fourth. Now it's 1/5 x to the fifth plus c. Okay,
so I just wanted to point out, just because there's no product rule doesn't mean that we're helpless for products with antiderivatives. We have many other techniques. So so you're right, sometimes you need U substitution, but sometimes all you need is algebra. Sometimes all you need is algebra. By the way, we can see here that there is no product rule, because remember, if we tried to use a product rule, we would have gotten this. Well, these clearly are not the same. What's x to the third times x to the third?
X to the 9.
X to the 6th, actually. Adding this, well, that clearly doesn't match this. And 1/3 times 1/3 is 1/9. So we just proved here that there's no product rule for antiderivatives. Okay, so what do you do in this case? Well, you might have to use U substitution, or you might have to do algebraic rearrangements. But you should keep in mind there is no product rule for antiderivatives, and the term chain rule really refers to derivatives. But when you said you could use U substitution, perhaps that was correct. Okay, so let's go back to your screen. Okay, that was good, just to clear up that confusion there. But you were right to label that as false. Again, there's no quotient rule for antiderivatives, so you labeled that as false. And E is true, you labeled that as the constant multiple rule. Okay, very good. All right, so you got all those correct. Let's take a look at number 2.
Okay. Yeah, I just noticed that I forgot to rewrite my expressions for the answer for all these problems.
So. Okay, well, we won't worry about that. That's good that you noticed that. So obviously that's not the most crucial thing in the world. I just think that's a good habit. So going forward, we'll work on that habit. All right, so let's take a look here. Negative. So your U is equal to sine of x. Okay, Um, So let's scroll down and look at your check. Okay, so how did that check work? Does it look like we got that problem correct or incorrect?
Well, it didn't match up to this. This was the one that gave me some trouble for some reason. I'm thinking maybe I made a mistake here.
Okay, yeah, so what was the
inverse.
result of our check? Did the check make it look like we got this right or wrong?
No, wrong.
Okay, good. Did you notice that when you did it the first time?
Yep,
Okay.
I just kept
All
going.
right. Okay. If you have time on those, it's always best to go back and check to find the mistakes. That's the whole purpose of the check. Let's see here. So I'll just tell you that the mistake is when going from the next to the last line of your solution. So I think if you put in a little time, you probably would have been able to find that. So that's one good that's one advantage of having this as homework. If you have the time to go back and check, you can do the check on your own time. So you can recheck it and see that it'll come out correctly that way. But that's one reason why it's good to actually be checking these, so then you can catch those mistakes. Obviously, that was just a careless mistake, and you can catch that with your check. By the way, I wanted to point out the way. So obviously, you'll have to erase that check and redo it, but let's not erase it quite yet. What's the derivative of the inverse sine of x?
1 over the square root of 1 minus x squared.
Great. Do you need the chain rule for that, or can you just use a simple rule?
We can just use a simple rule.
But it looks like you actually tried to use the chain rule there.
Yeah.
So that was a little unnecessary. Notice you can see it was unnecessary. So notice it's never wrong to use the chain rule. What happens when you use the chain rule when it's not necessary? You just get the same answer you would have before, because what's the derivative of u with respect to u? 1. It just drops out. So it just gives you an unnecessary complication. So but that's an interesting thing that we saw here. We never mentioned this before. It's never wrong to use the chain rule, but it's often an unnecessary complication. So this is an interesting example. This shows you what happens when you use the chain rule when you don't need it. It just puts in a derivative of u with respect to u, which just goes down to 1. Why did you use the chain rule here when you didn't really need it? Well, it's probably because you noticed that normally when you're checking the answer on these problems, you do need the chain rule, and that's true. Anytime you needed u substitution, you're almost always going to need the chain rule to check that. So that should have been another clue that we'd made a mistake, basically. The fact that you didn't need the chain rule was a clue, because basically u substitution is kind of like the opposite of the chain rule for derivatives. U substitution is kind of like the anti-chain rule for antiderivatives, so you're almost always going to need that. Okay, all right, so there's a couple things we learned there, how we can use the check there to actually catch those mistakes. All right, so let's see. 3. So in this next example, you really did need the chain rule.
Mm-hmm.
Okay, that looks good. Let's keep going.
Cool.
5e to the x, 5e to the x. It looks like when you on your check and on your solution you use the constant multiple rule. So did we need u substitution there?
No.
No, so that was just a trick question to make sure you were awake. That's important because when you take the final, you can't assume that every problem on the final requires u substitution. Although it's just like with the chain rule. If you do use, you could use u substitution there, and if you do it correctly, you'll get the same answer, but it should just be an unnecessary complication. But obviously, it's better not to use it when you don't need it. All right, so that's good that you were seeing that you didn't need the u substitution there. All right, then the tangent of x, sine over cosine, cosine, negative sine. So let's see. Negative sine Okay, and let's look at the check. Oh, that's the whole check. All right. 1 second. Okay, so go on.
Okay.
Tangent times secant squared. So u was secant. So how did you know that u equals secant x was a good substitution to make here?
Because we can break the function into secant x times tangent x, and if you use u equals secant x, the first derivative of secant x is secant x tangent x, and that is inside of our function.
Excellent.
Or inside of our integral.
Outstanding. Very good. Let's try another one. What happens? Write down u equals tangent of x.
Okay.
Would that be a good substitution?
Derivative of secant squared x. So if you use u equals tangent of x, then you would have u times. Yeah, actually, I think it would be good.
Okay, so I just wanted to point that out. Sometimes there's more than one substitution that'll work. Sometimes there's more than one substitution that'll work. There's nothing wrong with the way you did it. This one is a little bit simpler. This one's a little bit simpler, but the way you did it wasn't so complicated either. So either of those is fine here. How can you see quickly that this substitution will work? Well, what's the derivative of tangent x?
Secant squared x.
And you can clearly see that accounts for the rest of the integral. Okay, but like I said, I just wanted to point that out. There's nothing wrong with the way you did the problem. Okay, so let's continue.
Oh, that's weird. I don't know why I did that. Oh well.
So then taking a look at this.
I think I made a mistake here. That's not right. Although I get the right answer down here, so it should be 6. And then
now let me ask you a question. Why are you breaking out one tangent from all the other tangents? Obviously that's legal, but is it helpful?
I guess not. No.
Right. So you were confusing that with the trick that was helpful on the previous problem. Let's actually go back to the previous problem.
Okay.
It can be helpful to break out one of the secants. Why is it helpful to break out one of the secants here? Because when you break out one of the secants, it can pair up with the tangent to be secant tangent, which is the derivative of secant. It's hard to put it into words.
Yeah.
But the point is, secant tangent is the derivative of secant. So it helps to break out one secant, so you can have a secant tangent in your expression. But I don't think it's ever going to be useful to break out one of the tangents. Yeah. Breaking out one of the tangents isn't going to help you. So you were probably doing that a little bit just by patterns. Now, actually, as it turned out, that didn't hurt you though, because you ended up just putting them back together again. You actually did get this right, because you ended up just writing that you ended up with u to the 7th, right?
Yep.
Well, so what basically is that you just went back to calling it tangent to the 7th. So you just tried something and then you just reversed it in the next step. So that step was unnecessary, but you didn't actually write down anything was wrong. You wrote down one line that was wrong because you wrote down as tangent times tangent to the 7th. that was an algebra mistake, but you didn't actually, that didn't mess you up later on. Okay, so we may as well, though, erase that second line for your note since it wasn't really a necessary step. Not that, I'm sorry, the line above it.
Okay. So
your substitution is a good one. You're doing u equals tangent of x. What's the derivative of tangent x?
Secant squared x.
Is that in the derivative? I mean, in the integral? Yep. So that's a great substitution. That's a great substitution. We don't need to algebraically rewrite this. So let's go ahead now and substitute. What do you get when you put in that substitution? Yeah. Okay, what happened to the secant squared x times dx?
That
maybe you should write one more line. So the first line there should be u to the 7th times secant squared x dx, because usually we do it in 2 steps, and then you got rid of the secant squared x dx. Okay, so you did get the right answer. You kind of tried something that wasn't going to work, and then you kind of ignored it, and you did it the correct way. So it never really helps to break out one of the tangents. So we didn't need to do that in this case, because we already had the derivative that we needed, the secant squared x there. And then in your check, let's see, 8th, so 8, 7.
Yeah, I have a bunch of mix-ups here. It should be 8. But somehow I got the right answer, so I don't know.
One moment. Okay, yeah, well, what you have written down now is correct. You might want to go back and redo this problem again later, though, because it gave you some trouble. This wouldn't be a good one to mark. And try again. 1 second. Okay, so now it's coming out correctly. But obviously there were some confusions here, so it would be good to go back and try that again. Okay, so we can go on. All right, now this is the case where it helps to break out a secant, because you want to have a secant tangent term there in the derivative. So you end up with the u to the 4th. Let's see, 5. Okay, that looks good. Okay. Yeah, so number 9 was a trick question. You don't need u substitution for that, because it's just something that we know the simple antiderivative for. So that's good that you adapted. And the same for number 10. You didn't need u substitution for number 10, so that's good that you were not on autopilot and you adjusted there. All right, good. Then number 11, cosine over sine. So you plugged in u for sine. Okay, well, I would say that was a real challenging set of problems there from 5 to 11. It's real, from 5 to 10. It's real hard to keep track of the all the different techniques there. So there were a few confusions there, but overall you were getting those right. So especially number 7 would be good to go back and try again. But overall, number 7 you should try again. But overall, that was a good approach, and it's good that you took the time to check those answers there. Okay, very good. Okay, that's good. So that's good that you took the time to do those problems. Let's go back to my screen. Let's try this problem. Good. All right, let's see. So point to the line that says x dx.
Right here.
Yeah. Now I noticed you got rid of the x dx. How did you get rid of it?
Because we said that du equals 2x times dx. And I think that you can substitute up to, I'm not sure how to phrase it, but if it's almost the same, then, so maybe that's not right.
Yeah, that's a misunderstanding. That's a confusion of two things we talked about. So is x dx equal to du?
X dx equal, no.
No, it's not. So we can't substitute them in. That can't be
Okay.
right. It can't be right just to ignore that constant multiple.
Okay.
So
I guess,
how would we do that?
let's see. If we did use x squared plus 2, then 2x.
All right, well, let's talk about it a little. I just think maybe you're getting a little confused on this problem. So what you're remembering is we want to make a substitution whose derivative is in the integral up to a constant multiple. We want to make a substitution whose derivative is in the integral up to a constant multiple. So the derivative doesn't have to be exactly in the integral. It only has to be in there up to a constant multiple. So, so this was a good substitution. This is a good substitution because its derivative is in there up to a constant multiple. Now, that doesn't mean that we can ignore the constant, though. We don't ignore the constant. All right, now I think you're doing it correctly. The reason that we only have to have it up to a constant multiple is because we can use the algebra trick that you just used there. Okay? So...
let's see. Okay, so now we can say...
yeah, that's the line that was incorrect. So what are you substituting in for x dx?
For x dx, we're substituting in 1/2 du.
Good. So why was your original approach wrong? Because before you were substituting in du. But du is not the right substitution. The right substitution is 1/2 du. Okay.
Okay.
All right, let me think for a moment. Okay, so let's go ahead and rewrite the ditto lines for the last line there.
Okay.
Okay, if you wanted to, you could check that for homework, but you've already practiced that quite a bit. You'll find that it's easier to check these if you don't multiply the coefficients. So instead of writing it as 1/2 as 1/3, you'll find that it's easier to check if you write it as 1/2 times 2/3. Now, for your answer on the exam, maybe it's a little better to simplify. But when you're checking, it's easier to check if you don't multiply the coefficients. Maybe you've seen how that works out when you're doing it. Okay, so not that it's wrong to multiply them together. All right, so this one we got incorrect to start with. I think you were just getting somewhat confused on this because I think you've used this technique correctly before. That's just sometimes people lose their bearings a little bit on one problem. So what we've said in the past is that when you make a substitution, you want to make a substitution whose derivative appears in the integral up to a constant multiple. And on this problem, we were misunderstanding that. What you said was, oh, we can ignore the constant multiples. Well, it doesn't mean that you ignore them. It just means that it's good enough to have the derivative in the integral up to a constant multiple, because even if there is a constant multiple, we can use our algebra here to deal with it. So this is hard for me to put into words, but we're not ignoring the constant. The lesson here is not to ignore the constant. So here's the key thing. Let's see. Point to your third line.
Right here.
All right. I guess I'm at the second line.
Okay.
All right. So what do we have there? What part of that refers to x? We have x dx, right?
Mm-hmm.
So what you need to do up in your top right corner is solve your equation for x dx. That's the goal. Your goal is to solve the equation for x dx. So point to the second line in the top right corner. Is that equation solved for x dx?
No.
But that was where you went wrong, because you were acting as if it was. That was where you stopped the first time around. The first time around, you just plugged in using that, but that was incorrect. You had to take one more step and actually solve for x dx. So that's the approach. The approach is collect all the x's together in your integral, and then use your substitution to solve for that function of x, and then you can make the substitution. Okay, well, like I say, that's hard to put into words, but when we see the example, we can see how it works there. So we're not saying that we should ignore the constants. Okay. All right, so I'll go back to my screen. All right, so as always, these take a lot of practice. You can see it's easy to start to lose your bearings a little bit and forget what the approach is for some of those problems. Okay, so let's try this problem.
Okay, so Okay.
Okay, since that's our answer, let's write down what we solved for on the left. That's a good habit.
Mm.
Okay. All right, good. It would be a good homework exercise to check each of these, but we won't do that in the session to save some time, but it would be good to go back and check them. Again, that's also good practice with derivatives, since you'll need those derivatives on the final as well. Okay, so the key thing here is you were able to get the expression down. The only x's in your expression was dx. So you solved off on the right for dx. Notice you didn't ignore the 2. You had to include that in your solution. Okay, perfect. Very good. I'll go back to my screen. Okay, let's try this one.
Okay. Let's see. Okay.
Okay, so you got down to the point where the only x is in your expression was x dx. And what did you substitute in for x dx?
1/2 du.
How did you know that was legal?
Because that's what's left over in the integral.
But how do you know it's legal to plug in 1/2 du rather than 1/3 du or u cubed du or square root of u du? How do you know that's the legal thing to plug in for x dx?
Because we solved for x dx.
Okay.
Yeah.
Yeah. So you know it's legal because it says that right off to the right.
Right.
According to your equation on the right, what does x dx equal?
It equals 1/2 du.
So it's obviously legal to plug in 1/2 du for x dx because they're the same exact thing. So I just wanted to make sure that the logic of that step is clear. We're not doing anything weird or unusual here. We're just substituting in something that's equal to the x dx, and we know it's equal from the work that we did off to the side. So notice how you handled the 2 off to the side. You didn't just ignore the 2. You handled it algebraically. When you solved for x dx, the 2 turned into a 1/2, and you included that in your answer. Okay, that's fine. Very good. I'll go back to my screen.
Okay.
Let's try this problem.
One over x u to the 4th dx. Okay. Okay.
Okay, that's good that you're remembering to put in the plus c. We have to keep that in mind for full credit for these problems on the test. What does the c stand for?
C stands for a constant.
That's right. And you can see that when you check your answers, the c could be any constant, because what's the derivative of a constant?
0.
So obviously that could be any constant, and it wouldn't affect the derivative of the expression. Okay, so it's good that you're remembering that. So this problem you have to do a little algebra, splitting off the 1/4 and the 1 over x. So that's good. That was a good use of algebra. One thing that you're doing here that's good is you're rearranging the expression so all the x's are together. So what the key step here is when you wrote 1/4 integral u to the 4th times 1 over x dx. The key step is rearrange the expression so all the x's are together, Because that tells you what to solve for on the right. How did you know to solve for 1 over x dx on the right? Because that was the expression you were trying to get rid of on the left. So those are very important steps. It's important not to skip those. And that's good that you're doing that. Okay, that was correct. I'll go back to my screen. Let's try this one.
Okay. Okay, so the antiderivative of secant theta is secant theta, tangent theta. So if we pull out secant, okay. If we use u equals secant theta, the derivatives, antiderivative of secant, the derivative of secant theta, tangent theta. We see that, then we're left over with secant squared theta, or u squared. Okay, yeah, this works. Okay.
Okay, one thing that you did that was good on this problem is you recognized that the substitution isn't guaranteed to work. You have to test whether it's going to work. So you said, let's try u equals secant theta, but you recognized that it's not guaranteed to work. What would you have done if that substitution didn't work? If that substitution doesn't work, you just have to try another substitution, basically. So if you're, you can't force the substitutions to work. If the substitution doesn't work, just try something else. But in this case, your instincts were correct, and the substitution did work. This is a pretty tricky problem, because you have to see this trick of breaking out one of the secants out of the secant cubed. That would be a hard trick to think of from scratch, but fortunately we've seen this type of problem before, so we've seen that trick. So it's good that you recognize that we needed that trick here in order for the substitution to work nicely. All right, I think that's one of the hardest of the U substitution type problems that we've been working on, but you got that correct. That's good. I'll go back to my screen. Let's try this problem.
Okay. Okay, split it up. U equals natural log of x. Derivative is 1 over x. Solve for du, or for, yeah, solve for du. Or solve for 1 over x times dx.
Right. We're not solving for
Yeah.
du. We're solving for the expression, the function of x we need to get rid of. It just happened by coincidence to equal du in this case. Good.
Okay, and then use substitution. Antiderivative. Derivative of cosine is negative sine, so opposite. Okay? And plug it back in. Okay, and then I need to rewrite.
Okay, that's a good process. I'm going to make one suggestion, though. I noticed that what you did here was first you solved on the right for du equals 1 over x dx. Then you went over to the left and you rewrote the integral as integral of sine natural log x times 1 over x dx. But actually, those should happen in the reverse order. First, you need to get all the x's together in the integral. Only then do you know what to solve for on the right. So first, you should get all the x's together in the integral, and then only then should you go back and solve on the right. Now, in this case, it didn't mess you up at all, but if the instructor throws you a curveball, if they throw you a problem that's a little bit different than the ones you've seen, then it's important to use that process instead. So the point is first solve for the one, first get the x's together on the left, and then solve on the right. That didn't mess you up at all in this problem, but this problem was a little bit similar to the ones we've seen before. If the instructor throws you a little bit of a curveball, it'll be better to have that alternative approach, because that's how we, remember, we're not solving for du. We're solving for the function, we're solving for the x's that we haven't been able to get rid of yet in the integral, and you don't know what those are until you've rewritten the integral on the left. Okay, all right, well, that's a minor suggestion. Overall, that was a good process, so I'm going to go back to my screen. You got that correct. That was good. And let's try this problem.
Okay. So
take another look at my screen. I think you miscopied the problem.
Oh, yep. Okay. So
I think without that little 2, the problem would have been impossible to solve using the techniques we've talked about.
Okay, so now we can rewrite this as Okay.
Okay, that's right. That's the way to do it. Very good. I'll go back to my screen. Let's try this one.
Okay. Okay, so the derivative of inverse tangent of t is 1 over plus t squared. Okay, the derivative of inverse tangent of t is 1 over 1 plus t squared. And then u equals this. That's u. Antiderivative. Okay, cool.
So what were you solving for on the right-hand side of the screen? What did you solve for on the right-hand side?
I was solving for 1 over 1 plus t squared times dt.
Good. How do you know you have to solve for that? Because those are the t's that we haven't been able to get rid of yet in the integral. Good. So notice, again, we're not solving on the right for du. We're not solving for du. In this particular case, you did get du by itself, but that's just a coincidence. It's a coincidence that we happen to get du by itself there. We've seen many other examples where the du does not end up all by itself. So we're not solving for du, we're solving for the function of t that we haven't been able to get rid of yet in the integral. And you did that correctly. That's good. All right, I'll go back to my screen.
Okay.
Let's try this problem.
Okay. derivative of sine is cosine. Okay. Okay, so cotangent is equivalent to cosine over sine. We separate them, separate the fraction. Derivative of sine is cosine, so we can use sine as u. Solve for cosine theta, d theta. One over u times du. Antiderivative of 1 over u is this. And plug back in. Okay, cool.
Okay, good. That's right. Notice that this we wouldn't be able to get off the ground here if we didn't have memorized that cotangent equals cosine over sine. So that's something to keep reviewing until the final comes around. We need to keep memorized that cotangent is cosine over sine. So that's good that you remembered that. Okay, that's right. I'll go back to my screen. Let's try this problem.
Okay. Okay. So the derivative of x squared is 2x. Okay.
Excellent. That's very good. It's good that you remembered that you don't use the power rule here. You use the natural log as the antiderivative. The power rule doesn't apply to that function. You need the natural log. That's good. I'll go back to my screen. Let's try this problem.
Okay. All right, so okay. This derivative is 1. This derivative is 2x. Oh. Yeah. How do you do this? Okay, so we have that works. Antiderivative of 1 over x, natural log, absolute value of x, and then power rule for antiderivatives, plus your constant. Okay, cool. And then rewrite it. Okay.
Okay. All right. Well, that was very good. So as you figured out, this was kind of a trick question because it doesn't require substitution. As you figured out here, this problem doesn't require substitution. But that's an important thing to practice because remember, on the final, you can't just assume that all the indefinite integrals are going to require substitution. Presumably on the final, there's going to be a bunch of different types of indefinite integrals, some that require substitution and some that don't. So it's important to be able to tell the difference between them. So that's good that you were shifting gears here on this problem. In fact, not only does this problem not require substitution, substitution would not be helpful here, as I think you were kind of figuring out. You were figuring out there weren't really any substitutions that would be helpful to us on this problem. Okay, so I wanted to remind you of that. Don't assume that every single problem is substitution. You have to remember we actually learned a bunch of integration techniques earlier that might be on the final as well. So remember to keep in mind all the other integration techniques we've already talked about, not just substitution. So let's go back to my screen. So you didn't actually write this step down, but presumably what you were doing on this problem was, first of all, you did this in your head, and then you wrote it like this. Now, how do you know that this step is legal?
Because if you add the fractions together. Wait, actually, if you add the fractions together, then you get 1 plus x squared over x.
Okay, so is this step legal?
Yep.
Yeah, it really is. You didn't write this step down, but hopefully you were doing it in your head. So we can see that that step is legal. So how about on this problem? On this problem, could we rewrite the fraction like this?
Nope.
How can you tell that's not legal?
Because they don't have a common denominator, so you can't add them straight up.
Yeah, you can't add them together and get back to here. Is this plus this equal to this? Well, no. In fact, you can't add them at all easily because they don't have a common denominator yet. So remember, we've talked about rather than trying to memorize. So my point here is we shouldn't be memorizing that this is legal and this isn't legal. If we take small little baby steps, we can tell. We can tell what's legal and what isn't. If we do this in small steps, we can see this step is legal because we could reverse it and get back to where we started. And if we do this in small steps, we can see that this is not legal because we can't reverse it. So that's why on this problem, you might have said, I'm dividing x into 1 and x into x squared. You might have said, oh, I'm canceling the x into the x squared to get x. But that's not the best way to think about it. Even though you are doing that, that's not the best way to think about it. The best way to think about it is to take a smaller step and say to yourself, first, I'm splitting this up into the sum of two fractions, because we can tell that that's legal by reversing it. And here, you might try to cancel the x's. You might try to cancel the x's, but that's not the best way to think about it, because it's hard to tell if that's legal. Instead of saying you're canceling the x's, it's better to say, well, I'm splitting this up into two separate fractions, because then you can tell that's not legal. You can see this is not legal because these don't add up to get back to where we started. Okay, so it's good to have these two problems together in your notes. Notice that these two problems look very similar. These problems look very similar. Are these two problems solved using the same approach?
They're not.
No, even though they look almost identical, we used completely different approaches for these two problems. So that's something you need to watch out for on the exam. Very small changes in the problem can make a huge difference to how you're going to have to solve it on the test. Okay, well, we just did about 10 of those indefinite integrals in a row, and you not only did you know how to get them all right, but also very important, you didn't make any careless mistakes. So that's very important as well, to get to the point where you can not just get the problems right, but get them right without making careless mistakes. But I think you did that, so that's excellent. That's good that you were taking time and avoiding mistakes there. So I think we made some good progress on that substitution method. I think it's time for a math joke. So let's see. So these two mathematicians walk into a bar. And they're sitting there in the bar, and they're having an argument. And the first mathematician says that most people know almost no math. Most people don't know much math. And the second mathematician says, no, you're not giving people enough credit. People really know a lot more math than you give them credit for. And the first mathematician says, no, you're fooling yourself, man. Most people know hardly any mathematics. So they go back and forth. They're arguing about this for a while. Finally, the first mathematician gets up and leaves to use the restroom. And while the second mathematician is sitting there at the table, he has an idea for a trick to play on his friend. So he calls the waitress over. So the waitress comes over, and the mathematician says, Miss, could you do me a favor? When my friend comes back from the bathroom, I'm going to call you over here again, and I'm going to ask you a question. And I want you to say that the answer is 1/3 x cubed. Can you do that for me? So the waitress says, 1/3 x cubed, 1/3 x cubed, 1/3 x cubed. Okay, I think I've got it. So anyway, in a few minutes, the first mathematician comes back from the restroom, and he sits down again, and they start arguing again about whether ordinary people know a lot about math or not. So the second mathematician says, I'm going to prove to you that people know tons of math. And he calls the waitress over to the table again. And he says, Miss, I'm going to ask you a question. What is the integral of x squared? And the waitress screws up her eyes, and she furrows her brow, and she looks like she's thinking about it. And finally she says, the integral of x squared. The integral of x squared is 1/3 x cubed. Well, anyway, the first mathematician is amazed, and the second mathematician is very pleased with how well his trick worked out. And the waitress is walking away from the table But then suddenly, as the waitress is walking away, she turns and she says over her shoulder, plus a constant. All right. So that's your payoff from the course. The payoff from the course is that without this course, you could not have appreciated that joke. Now you're mathematically literate enough to get the joke. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.